My name's Steve Regan, computer science teacher, a bit of an electronics amateur. I'm bodging my way through a retro build of a Z80 computer. This is my second video in the series, although a lot has happened since the first series, and I've been logging my progress on Facebook. So let's get into what's happened since the last video. So I'm just going to skew this down so that you can see the actual board here and focus it in. Okay then, so what we actually done? Well, the last time that I set up this video, I basically had the Z80 on the board and this circuitry here, and that was actually timed off the pin here. The timer pin was actually timed off an arduino, so I wrote a little program in C to allow it to time the processor. But since then I got delivery of this little tiny chip here. It's not very visible unless I lift the board up there. I might have to tilt it to the side so you can actually see it. It's immersed in wires. It's a little 555 IC timer down there. Now what that does is it works at 1 megahertz, and the processor is actually a 6 megahertz processor, but that's enough really. It's more than enough for what I need. I've actually clocked that down to about 300 hertz in order so you can see the LEDs going, but I'm going to replace that later on with a more sophisticated timer that will clock it right to 6 megahertz. But for now, what that's done, this circuitry here of capacitors capacitor and resistors is actually timing the actual processor. So it's actually like a metronome. When you're doing music, it just it puts out beats of which instructions can then be fed to the processor. Okay, I've also added this reset circuit down here. This is a Schmitt Trigger here, which is a small chip that I've used on previous projects to take debouncing out of buttons, so for button presses. But in this time, what I'm using it for is an inverter. I wanted to be able to press this button here, and instead of putting power in to the reset switch, I wanted no power at all, because its current state is the fact that it is pulled high, which means that it's always on. As soon as you take the power off, it resets the Z80. It's a bit more convoluted than that because there's different reset modes, but for now it does what I need it to do. It can be a bit temperamental, but that's because of the quality of that switch there plugged into the motherboard and not the circuit itself. Okay then, so I'm going to switch it on, and you can see that it will do exactly the same as what it was doing before. It's sort of counting in binary up. Like I said, this is the clock cycles here. That's the number of machine cycles that's being clocked at, and that flash is about 4 times slower, like I said on the last video, and that's because it takes 4 of these actual instruction cycles to actually do one instruction, basically. So for every clock cycle, this particular no instruction takes 4 cycles to fetch, decode and execute. Probably got 2 decode or 2 execute parts to it, depending on the instruction. Anyway, so that's it working without the Arduino anymore. That little chip there is timing it, and that's really crucial to the operation of a CPU, basically. So here we have our reset circuit here, and now the reset circuit, I'll just like I said, it's a little inverter here, so when I press that button, it sort of draws the power out with this capacitor and basically sets the processor to low. So if I press that now, just watch the LEDs, it sort of switches them all off and then it starts the timer again. That wasn't a trivial circuit because I couldn't really find on the internet how to do that. I just had to use the circuit diagrams and try and work out with LED lights how I could switch a light off rather than switch a light on using it. But I managed to do it, and there are more elegant ways of doing it, but I only had that chip, so I decided to use its inverter facilities. Quite a versatile chip anyway. So anyway, so that's that part. So it doesn't do much at the moment. Just to recap, the program is being hardwired into it, no instruction, with these resistors drawing down the power. So it's 000 onto the data bus. And then we've got part of the address bus. It's a 16-bit address bus that goes all the way around this side. But I've only used these 7, like I said on the last video, to actually show you what's going on. And it's cycling through all the machine, all the addresses that it thinks that is calling to memory, basically, to pick up data. So that brings me neatly on to what I did next. I said in the last video I was waiting for a number of more IC components to turn up, and they have. And we've got this one here, which is an EEPROM, which is electronically erasable programmable read-only memory. And this is, once I get a programmer, I will be able to put machine code instructions here that will remain in the chip once the power is off. And this one here is a RAM chip, so that's non-volatile, meaning that you can remove the power and the code still stays in there. Most devices need this in order to start up and actually know what to do and have instructions embedded into them. So I'll be programming that later on to function my computer, Z80 retro computer. You've got a RAM chip here, or this is a SRAM chip, which is static RAM. I'm not using dynamic RAM because it's a retro computer, but also it would need a larger circuitry so that it could refresh properly to make it dynamic. And but this one is an older style chip. It's good enough for what I'm doing, hopefully, for this project. Down here is a small chip, and this is quite an important one because I'm going to have to show you a little bit of a diagram here to show you about memory. I'm just going to switch those lights off a minute so I can go into this. So basically what we've got here is some diagrams of memory. So first of all, I said it had a 16-bit address bus. So it can carry 16 zeros or 16 ones, or any combination of them. So what it means is that the Z80 computer can address, and that is both RAM and ROM together, can address between 0 and 65535 memory addresses, which in total is 35536 memory locations if you include the 0. So if you put all the addresses on address bus to 1, that's the top of the memory, and the bottom of the memory if you set them all to 0. Okay, so that's made up of 2 parts: ROM, read-only memory, and RAM, random access memory. And the memory chips that I've got are a bit over the top because you can't. Well, I could have gone and bought some retro memory chips. But basically, what I've done is I've bought these little memory chips here. Okay, and there goes the pins on the back. Okay, that's a SRAM memory chip. And that is 256 kilobytes of storage space, and so is my EEPROM. That is also 256 kilobytes. But like I said, because of the nature of a 16-bit computer, I can only really address at any one time 64Ks in total of this. So it's partitioned into 32K chunks, as you can see there. So each chip has 32Ks, and I could choose to use one portion of this and one portion of that, making a total of 64. Now, if I wanted to instigate some form of paging, for example, I could have, say, BASIC programmed into that. I could have another operating system like CPM or something like that I wanted to put in there. So I could have different sort of profile ROMs which I could call. I could also have different segments of or pages in memory which I could call in and out. The Spectrum 128 did that. It could call in 128K of memory by paging parts of RAM in and out, but I'm not going to do that. I'm going to just use 64K. It's way beyond my capabilities. So what I'm going to do now is just show you basically how I've got to do some form of testing to make sure that my memory works, and that wasn't as easy as I thought it was going to be honest, because I thought that I would be able to just link it all up and do some experiment. But it's all, I haven't got a ROM programmer, so I can't actually program any instructions in it. And because random access memory, or SRAM, loses its memory once you turn it off, I had to devise a system that I could actually test whether it worked. So basically, I put the chips on I put the chip on a breadboard here, as you can see. There it is, smothered with wires. It's actually in there somewhere. Okay, and there's the schematics here of the actual chip and how it works. So just let me look over to here. So this is the actual chip here, and it's got a little notch up this end. So this is this end of the chip here, and that's the back end of it. So that's the top end, and that's the back end of it. And I've got some address lines down the side here. So I've got some address 0, 1, 2, and 3, and 4 this side. I've got 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 on that side. So 0 to that, there's 15 address lines on there. Okay, basically making up my addressable code. So it's 0 to 14. I've also got some data lines here. So I've got IO 0, 1, 2, 3, 4, 5, 6, and 7, which is my 8 address lines. I've got ground, which is, and power. So that's how I can power the chip. I've got a pin here, which allows me to write to the chip, so I can put something in it. There's an output here, that's OE, which allows me to output information from the chip so I can see what's going on. And this one is a chip select, basically. So that means that if I want to put data on a data bus from another device, like a keyboard or a display, and I don't want it to go to RAM, then I can bypass this chip altogether. So these are going to become useful in the project. So how have I operated this? Well, it's not as easy as I thought. I spent hours trying to devise some sort of system in order to be able to do this. And what I came up with was an arduino project. So basically what I did was wired in here some of the wires into the address bus here. So all these wires that come from the Arduino are going into the address bus of the chip. And I've also got on this side 4 wires which are hanging loose at the moment, and I'll tell you why that's so in a minute. And they're going to go into 4 bits of the data bus, which these LEDs are all plugged into. So what I devised was I wrote a C program in here, written in C. And what I hoped to do was I hope to alter 2 addresses in memory. So if we go back to this schematic here, what I've done is, say this is address 0 and there's address 8, and remember we've got 65535 addresses, so 65,535 addresses, but I'm only interested, I'm going to put something in address 0, so that's 0000, and something in address 4. Now, what I found out was that the rest of them aren't empty. They can have some sort of random value in it, which meant that when I was initially testing, I thought it was going wrong, because it was, I thought that I just have to see what was in that one and compare it with another one, and that would be empty, but it had all sorts of random values in it. So you have to sort of refresh and initialize the memory if you want zeros in every location. So what I had to do was put a value in address 4 and force it to all low, so it's 0000. So it's a simple little experiment. It's a program. What it does is I first of all write to the chip by putting these wires into the 4 pins on the end here, write to the chip and put 10010000 in there, and those, it will light up. These are the pins, so it should light up 1. Those 2 should be off and that one should be on. So I've not used the lower values here. And then I've written the zeros into address 4 using a C program. So once I've done that, I've then got it to wait 10 seconds while I unplug all these, because I don't want to be reading and writing to the same one, and then it reads the chip. So if I power it on straight away, if I power it on, you can see that the program's already in it, but unfortunately, because the program's already run, there's absolutely nothing in the chip at all. There's nothing there. So basically it won't come up with anything. So I'm going to put these wires in now here. I've got to get the right ones in the right place. So I've got that one there, and the next one goes in there. So I've got to get the right pins in the right slots, or else it will not work properly. So that goes in there, and then the third wire, just got to make sure it's the right one, because it goes completely wrong if you get the wrong wires in the wrong slot, and that one in there. Now what I've effectively done is put those wires into the data lines there, and now I'm going to, through the Arduino board, I've got output 13, which is the write output, so I'm going to set that to low so it will write. I'm going to set 11 to high so it won't read, basically, and 12 I'm going to set so that it selects the chip, basically. And then once I run the program, which I'm going to do now, so you'll see the Arduino flash as it starts to write the program to the chip. It should be flashing in a minute. Here you go, started flashing there. As soon as the light comes on, I've got to unplug these. I've got about 10 seconds to unplug these, put it to one side, and then we just wait for the 10 seconds to come up, and there we've got it. So what that's doing now is reading address 0, then address 4. Address 0, address 4. So what I've successfully done is I've programmed 1001 into some of the address lines, and I've programmed 000 in it, and it's just cycling through with a second in between through that. So what does that do? It just proves that I can write to any segment in the memory and then compare it with another segment to know that I've actually put data in the chip. So what I've got to do is set up the memory properly, and that will be the subject of the next video.